we're going to look now at the difference quotient, which really is the average rate of change restated. So the difference quotient is derived from the average rate of change formula. And this new look is using calculus to better perform and describe what the next process that we will not talk about in this class. So there's a process that is undertook in calculus. And therefore, that's the reason for doing this. So first, we're going to start off with the big change is what's sitting right here. We're going to call this thing H. Okay, so we're going to call that difference H. And to kind of follow through with what we really want to do is I'll call this right now A. Just to derive that formula as it looks like. So I'm going to call x1 A. So I'm going to let x1 equal A. So what are we doing here? All we're doing is changing a letter. And I'll explain in a minute why. And now that I've done this, I'm going to solve for x2. So it means I'm going to add A to both sides. And when I do that, I have the following. So it seems like all we've done is change things and change variables. And we have. The question is, what is this going to do for us? It's a way of re-expressing this. So if I follow what I have right here, x2 is really now h plus A. If I continue replacing things, x1 is really A now. And we established that the difference, x2 minus x1, is really H. So there you have it. This is now called the difference quotient. And what this says is really the A is a starting point. And the H is how much we're changing from that point. It's a distance we move from A. So really all we're doing is re-establishing a few things, but we're doing still the same thing. We're looking at starting here and ending here, except now we think of it from the terms of how much did we move by? Why do we do this? Again, in calculus, it's better explained. Right now, we're just kind of really focusing on the meaning of the average rate of change and also how to simplify these type of statements when we replace our variable with a more complicated version. All right, so we're going to use the difference quotient, find the average rate of change for a linear, quadratic function, and a simple rational to give you a sense of how this works. So I'm going to, for example, do this example twice from two different perspectives. Okay? So let's first find the average rate of change for the equation in the interval x to x plus h. Notice I haven't, I'm still leaving this as x, but how would this look like if I kind of did it from this perspective? From this perspective, then it would look something like this: A plus h. Look at my starting plus and then just go kind of a distance. Right? But these are locations on an interval. So that's what this is saying. So let's actually do it from that perspective. Okay? And I'm going to use this equation right here just to get you to see that no matter how you're looking at it, it's sort of the same thing. So if I did that from the average rate of change perspective, what I'm looking at is applying that on this interval. So this is where I end up at, x2. I'm assuming right now, from this perspective, that x2 is greater than x1, just to make, again, life simple. It doesn't have to be that way. No, but this just makes life simple for us. So clear, but here on this interval, that's exactly what the thing explained. So that gives me a better sense of where I'm going to dump these two. So I'm going to dump a plus h, which is the bigger one here. Okay, so I'm applying that formula. And then the first one, which is a. And at the bottom, I say, hey, subtract the second component from the first. So the first component is a plus h, subtract second component, which is just the a. So notice again, all that matches. This is just the slope of a line. But using this function notation to kind of grasp other functions that are not linear. So now I can look over here and start applying what I just did, but to this function. So now to do this, here's what I suggest you do. Write down what you're about to do. So here in this first portion, this first function, I'm putting inside a plus h, and now I'm going to put here a plus h. I'm going to subtract, and this function has one component, two components, and I'm subtracting both of them, so I need to put parentheses here in order to accomplish this. So again, what I want to do, 5, a big hole where the variable used to be, plus 1. And now I'm going to dump in that a right here. So notice the way I'm ordering these so I won't really mess up. Here at the bottom of this denominator, I can actually just simplify this. What's a minus a is 0. So what have I left? H. And voila. Notice there's a formula that this new one we've derived. So I'll come over here and just now simplify. 5, distribute my 5, so then we have 5a plus 5h plus 1. Here I'm going to distribute, quote unquote, distribute or restate the subtraction going on. So it's 5a subtract 1 all over h. So again, 5a minus 5a is 0. 5h, 1 subtract 1 is 0. So what do I have left? 5h. I cancel the h's and I'm left with 5. No surprise, because what is this average rate of change is really the slope of this line that we're connecting, right? Because what is this all about? What we're saying is, well, I started A, some starting point. I move some distance. What's that distance between here and here? We call that h. So I'll take a and add h to get to the next position. And let's say that the graph just looks like this for fun. So really all I'm doing now is connecting these 2 points and finding the average rate of change. That's all that I'm doing. My y's, my x's. But in this case, the equation is not a curve like this one, it's a straight line. So it matches the red line right here instead. So what's the slope of this function? Well, remember this is just a linear equation. The slope is 5. Now what is the slope? Well, the slope is for a linear equation. This happens to be linear, which of course, then the average rate of change and this match. And they're the same thing. Okay, that's all. So now what would this look like? So I'm going to call this next one example 1b. And what happens in example 1b? Well, we're going to just use the following. Using f of x, which equals 5x plus 1, apply the difference quotient. and simplify. Okay, so I'm going to use that as my function. So again, what's my, so I'm going to write the difference quotient down. And when I do that, what happens? Well, really, it's exactly, isn't it, are we doing the same thing? Yeah, that's what I'm trying to point out. So again, notice I'm going to write this down. Okay, now I'll write again, keep looking over here. This is my template. I have to keep looking over here and writing things down and matching, matching, matching. And now, again, here are the functions. So I have to look here, and everywhere I see a variable, I'll put in a big open parentheses. And now I need to figure out, okay, what did I replace that variable with? So I need to look up here and write, oh, it's h plus a. Here I replaced it with an a. And go, wait a minute, isn't that going to result in exactly the same thing that we just did? Yeah, yes, it is. And I can stop right here because it's going to come out to exactly the same thing. Are the steps any different? No. I mean, look at that. So this is two different ways of stating it. Sometimes you'll see a question say apply the quotient theorem, and that's all they're trying to do. Or they might say evaluate the quotient, evaluate, and they'll may give you that formula, this formula, and say for this function. And then that's all you'll do, which is the same as what you did here. Okay. Or it might just say, look, find the average rate of change for blah, blah, blah. And again, you just follow them the formula, put in the two endpoints, and the process is exactly the same.